So today my mom asked me why my room was so messy, and I told her, the universe is against me. The universe tends towards chaos. She didn't buy it and I had to clean my room anyway. But why does the universe act in this way? Why does heat move from hot to cold? And why does smoke disperse into the atmosphere?
The answer is entropy. And while you might have commonly heard of it as the measurement of disorder, entropy is so much more than that.
Let's play a game. I'm going to put 18 white and 18 orange balls in this box and shuffle them. Try predicting the order. Ready? Were you close?
Now most people would pick a combination of balls where they're evenly spread out. And there's a simple reason why.
There is only one combination where there are 18 balls on the left side. But there's as many as 160 million combinations when we introduce a little bit of disorder. If I'm being honest, that wasn't much of a game. It was an explanation for something that happened to me today. I gave my brother some ice cream yesterday, and I woke up today to see the ice cream completely melted. Let's go back to our original game. The orange balls represent the smallest, indivisible heat energy from the environment. We'll call this quanta. Entropy is just a measure of the spread of energy. Right now, the energy has not spread, giving it a low entropy, but as time goes on, the entropy increases, as the energy spreads right into the ice cream. The macrostates are the overall combination of balls in the box, and the different arrangements of balls in the macrostates are called microstates.
Entropy is often called time's arrow, as it can only increase with time. If it could decrease, my brother's ice cream should be able to unmelt itself.
So, why doesn't entropy decrease? In our experiment, the probabilities for the balls to remain ordered after being shaken is already less than 1%, but when we scale this up to more realistic quantities, you can see that the probability for the balls to remain ordered is pretty much zero. You see, entropy only increases because it's significantly more probable for energy to be distributed in a disordered state than an organized one.
But why is entropy important?
The concept of entropy was created by Rudolf Clausius in the 19th century as a way to improve the efficiency of engines. You see, energy is only useful when it's available in a low entropy form. When we have particles that move from a lower entropy to a higher entropy, we can use that to extract work, even though the amount of energy in the system is still the same. Moreover, entropy gives us the reason for the Big Bang. At the start, the universe was this extremely hot, dense, and small ball of energy, and it would have stayed this way if it weren't for entropy. The first law of thermodynamics tells us that energy must be conserved, but energy will still be conserved regardless of whether the universe expands or decides to stay the same. But the second law of thermodynamics, by using entropy, tells us that the capacity to do work over time decreases.
This tells us that the universe must distribute its energy over time, which can only be done by rapid expansion.
Without the concept of entropy, the universe could not act or evolve. If you think about it, time could have only existed because of entropy.